All right. Another type of function that you saw in pre-calculus and was an important type was a type of function called piecewise functions. So piecewise function, when you have a function of the formula, say f of x equals usually more than one formula. Let's say one formula. Maybe I can describe it this way, that if the formula for the function f depends on the value of the input x, then f is called a piecewise function. So they say usually f of x equals, some formula, if x, for example, bigger than some number, another formula if x, say, between two other numbers, and so on. So this is a general form of a piecewise function. So for example, let's say f of x equals x squared if x bigger than or equal to 3, and let's say minus 2x minus 1 if x less than 3. Find f of 3, f of 0, f of 5. So for f of 3, if you want to find f of a number, you have to look at whether that number is bigger than or equal to 3 or less than 3. According to the definition of f, if the input x is bigger than or equal to 3, then you have to use the first formula. And if it's less than 3, you have to use the second formula. So here f of 3, well, 3 falls in the first category. It's bigger than or equal to 3. So we have to use the first formula. And then the output will be 3 squared, which is 9. And f of 0, 0 falls in the second category, is less than 3. So we have to use the second formula, minus 2 times 0 minus 1, which is minus 1. And then f of 5. 5 falls in the first category, is bigger than or equal to 3. So we have to use the first formula, which is 5 squared, and 5 squared is 25. Okay, another important concept you learned in pre-calculus was the concept of one-to-one functions. So f is called the function f. It has to be a function, first of all. So if you want to have a one-to-one function, first of all, you need to have a function. And once you have a function, then you can determine whether it's one-to-one or no. So the function f is called one-to-one if f has no repeated outputs. has no repeated outputs. Or mathematically speaking, we can say that f is 1-to-1 if f of, let's say, a equals f of b, implies that a is equal to b for every a and b in the domain of f. So remember, each function has inputs and outputs. So if a function has no repeated output, then the function is called 1-to-1. So no repeated output means what? So depends on the type of function. So for example, let's say if the function or the rule that basically we are talking about is the dinner, for example, you eat on each day. Let's say if the days are the inputs and the dinners you eat on each day are the outputs, then if you, let's say, eat same dinner on 2 different days, let's say you eat pizza on Saturday and Tuesday, for example, then this function, which assigns the dinners to days, is not 1-to-1 if you eat same dinner on 2 different days. But if there is no repeated output, let's say you eat different dinners each day, then the function is 1-to-1. I'll give you also a mathematical example, but why is this the mathematical definition of a 1-to-1 function? F of a equals f of b implies a equals b. F of a equals f of b means if 2 outputs are the same. Remember, x is the input, f of x is the output, right? So f of a equals f of b means if the 2 outputs are the same, can we conclude that the inputs are the same as well or not? If we can conclude that the inputs must be the same, but then that means we do not have any repeated output, because if the 2 outputs are the same, the inputs are also the same. So it's just one output, it's not a repeated output. When we say repeated output, means the same output happening with 2 different inputs. If the input is the same, of course the output is the same, then it's just one output and of course one input. So if from equality of outputs you can conclude that the inputs must be equal, then the function is 1-to-1 because there is no repeated output. But if you have 2 equal outputs, but the inputs are different, well, then that means you have a repeated output and the function is not 1-to-1. So if this implication is valid, then the function is 1-to-1. If this implication from f of a equals f of b, because some people, I remember the exams, they think that 1-to-1 function means f of a equals f of b. No, 1-to-1 function means whether this implication is a valid implication or no, whether we can conclude that from equality of 2 outputs, can we conclude equality of inputs? Is this implication valid? If it's valid, then it's 1-to-1. So the 1-to-1 function is not same as f of a equals f of b. 1-to-1 function means if f of a is equal to f of b, can we conclude or imply that a is equal to b? If yes, then the function is 1-to-1. So let's look at an example. Let's say f of x equals 2x squared plus 1. This function f is not 1-to-1. If you want to show that it's not 1-to-1, you have to show that it has a repeated output, because remember, if it is 1-to-1 if it has no repeated output. So this function is not 1-to-1 because it has a repeated output. And what is the repeated output? Repeated output means what? It means 2 different inputs with the same output. So for example, let's say if I use input x equals 1, how much is the output? The output would be y equals f of 1, which would be 3. So if the input is 1, the output is 3. But Is it possible that another input also leads to the same output 3? The answer is yes. For example, x equals -1. Then the output for -1 is also 3. So see, 3 is a repeated output because same output for 2 different inputs. So f is not 1-to-1. F is not the 1-to-1. We can say because this. So another example, let's say f of x equals 3x minus 2 is 1-to-1. How can I prove that it is 1-to-1, this function? So tell me, can I say that, for example, I want to show that this is 1-to-1. So how about if I say, let's say x equals 1, then f of 1 will be 3 minus 2, which is 1. And let's see if I use x equals -1, f of -1 will be -3 minus 2, which is -5. And 1 and -5 are not the same. So can I conclude that the function is 1-to-1 because it has different outputs for different inputs? So is this a correct way to prove that the function is 1-to-1? The answer is no, this is not correct. So this is a wrong solution. Why is it wrong? Because, you know, in mathematics, to prove that a statement is valid, we must prove in general and not with examples. However, if we want to prove that a statement is false, we can provide one example called the counterexample. Okay, so our strategy in mathematics, it really depends on whether we want to show that the statement is true or we want to show that the statement is false. If we want to show it's true, we cannot do it with examples. It has to be in general. If you want to show it's false, one example is enough, which is called counterexample. So here we wanted to show it's not 1-to-1, so we used example of 2 different inputs with the same output. But here we want to show it is 1-to-1. So examples are not enough. Even if you give 1,000 examples, still not enough. It has to be proved in general. In general means what? Means with letters. So you use letters. Let's say X, or in this case, we call A and B, or you can call X and Y. It doesn't matter. You can choose the letters yourself. But when you say proof in general, it normally is done with letters. Okay. So in this case, and so with letters and using definitions, you have to also, of course, use the definitions. So what was the definition of a 1-to-1 function? The correct solution here solution. Let f of A equals f of B, right? So we said that the function is one-to-one. If f of A equals f of B implies that A is equal to B. So f of A equals f of B means what here? So f of A is 3A minus 2 equals 3B minus 2. And then if I add 2 to both sides, I get 3A equals 3B. And then divide by 3, I get A equals B. You see, the proof is in general. We started from f of A equals f of B, and then after some calculation, we proved that A is equal to B. So this means that the function is one-to-one. Another important concept you learned in pre-calculus was the concept of invertible functions. The function f is called invertible if there exists another function g such that FOG is equal to identity function and GOF is equal to identity function. So I can compare this with FOG equals identity function and GOF equals identity function. I can compare this with the inverse of a number. So for example, inverse of 2 is 1 over 2. Why? Because when you multiply 2 with 1 over 2, you get 1. Or inverse of 3 is 1 over 3, because when you multiply 3 and 1 over 2, you get 1. So f is called invertible if there's another function g such that when you compose them, so instead of multiplying them, here we have to compose the function. You know the composition of two functions, like FOG of x means f of g of x, right? So recall FOG of x is equal to f of g of x. So this is the meaning of composition of function. An identity function is a function that is neutral, meaning that the input, if the input is x, the output is also x. So I was saying that instead of multiplying, we have to compose the functions, and instead of getting 1, we have to get identity function. So identity function has the role of 1 here. Because it's neutral, right? So what is the important feature of 1 in the set of real numbers? It has the feature that when you multiply it with anything, 1 times any x is x, right? So identity function is also neutral, meaning that if the input is x, the output is x. So if there exists a function g that FOG is identity, which is neutral element of the functions, and GOF is also identity, which is the neutral element of the function, then f is called invertible, and the function g, in this case, g is called the inverse of f. The inverse of f, and is denoted by f inverse. F inverse means inverse of f. So what does inverse of a function do? So intuitively, F inverse changes or interchanges inputs with outputs. Okay, so see X, so let's say you have an input A and the output is B, which is f of A. Now, when we talk about F inverse, it reverses the process. Inputs becomes outputs, outputs become inputs. So when we talk F inverse, in F inverse, B is the input and A is the output. So this is what we said. So that f of A is equal to B if and only if A is equal to F inverse of B. So this is the important feature of inverse functions. So let's look at an example for inverse functions. For example, let's say f of x equals 3x. Find f inverse of, let's say, 6. F inverse of 6. Well, f of 6 is easy to find. F of x is 3x, so f of 6 means 3 times 6, which is 18. But what is f inverse of 6? Well, to find f inverse of 6, we can use this connection that we expressed here between a function f and its inverse. So if I call this one, let's say, star, so by star above, we can say that, if I set f inverse of 6, so let's say this is like my B here, right? So if I call it A, so this is same as saying that f of A is equal to 6. And f of A, how much is f of A? F of x is 3x, so f of A is 3A. 3A equals 6, and then this means A is equal to 2. So f inverse of 6 is equal to 2. Well, this is not surprising, right? Because f of x is 3x, right? So how much is f of 2? F of 2 is 3 times 2, which is 6. So if the input is 2 for the original function f, if the input is 2, the output is 6. Now for f inverse, input becomes output, output becomes input. For original f, input is 2, output is 6. For f inverse, input is 6, output is 2. Okay, so in general, how do we find a formula for f inverse? So that's one question. And another question is, which functions are invertible? So two important questions here. Question 1, which functions are invertible? So the answer is Do you know which functions are invertible? So f is invertible if and only if f is 1-to-1. So 1-to-1 functions are invertible and invertible functions are 1-to-1. So to answer whether a function is invertible, you just need to simply check whether it's 1-to-1 or no. And we already explained how to check whether a function is 1-to-1 and how to check whether a function is, or how to check a function is not 1-to-1. How should we write our solution in each case? So this is one question, and question 2, if let's say y equals f of x is invertible, how do we find its inverse? So we said inverse of a function changes input with output. So if originally y is given in terms of x, now if you want to find f inverse, you need to find x in terms of y. So the answer is find x in terms of y. So for example, here, I can give another solution for this. We want to find f inverse of 6. So solution 2, find x equals f inverse of y. Then plug in y equals 6. So f of x, so see we have y equals f of x equals 3x. And we just said that to find the formula for f inverse, we need to find x in terms of y. So how much is x is in terms of y? Y is equal to 3x. So how much is x in terms of y? So that means x is equal to y over 3. X is equal to y over 3. So that means x equals f inverse y equals y over 3. And once we have f inverse of y, the formula for f inverse of y, we can easily find f inverse of 6. We just need to simply replace y with 6. So we get f inverse of 6 equals 6 over 3, which is 2. Which is the same answer we got previously. Okay, and then one important example of inverse functions that you saw in pre-calculus was about logarithms. Logarithm is the inverse function of an exponential functions. So exponentials and logarithms. So what is an exponential function? An exponential function is a function of the form let's say y equals f of x equals a to power x, right? Where a is positive and a not equal to 1. So a to power x, so this base exponential function means a function that the variable appears in the power. If the variable appears in the base, like x to power a or x to power m, so then that's called a power function. And a special case of power function is a polynomial. So for example, x squared. X squared is a polynomial. The variable x appears in the base. Now for exponential function, the variable x appears in the power. So if the variable x appears in the power and the base is a constant, fixed constant, and not any constant, the base has to be positive and also not equal to 1. Why should it not be equal to 1? Because 1 to any power is 1, right? So we want to avoid that trivial situation. And why shouldn't be negative? For example, because this power x could be anything, could be 1/2, for example. 1/2, then we will have square root, right? And power 1/2 means square root, and square root of negative numbers are undefined, at least in the set of real numbers. We don't want to go into complex numbers in this course. So that's why we're saying that the base has to be positive and not equal to 1, and the variable x appears in the power. So a function of this form is called an exponential function. For example, you could think of y equals 2 to power x, or let's say y equals, for example, let's say 1/3 to power x, and so on. Now, logarithm function is defined as the inverse function of this. So f of x equals a to power x. F inverse of y is denoted by logarithm y in base a. So logarithm is just another notation for f inverse in the case where the function f is a to power x. Okay, so a to power x, let's say if I call it equals b, right? So so this is equivalent with saying that logarithm b in base a is equal to x. According to f of x equals b is same as saying that f inverse of b is equal to x, right? So this is what we said about the inverse of a function, that they interchange input with output. So in the original function, x is the input, b is the output. Now for the new function, b becomes the input and x becomes the output. And the inverse function, in this case, we said is also denoted by logarithm in base a. So a to power x equals b is equivalent with saying that logarithm b in base a is equal to x. So for example, and let's say if you want to find logarithm 8 in base 2. Logarithm 8 in base 2. So let's say if I call this formula, let's say I call it formula 2 star. So this one, if I call it x, right? So y2 star. So if I call this one x, then this formula says that this is same as saying that a to power x is equal to b. Now my a is 2, So this is same as saying that 2 to power x is equal to 8. My b is 8. Logarithm 8 in base 2, so my b is 8. 2 to power x equals 8. And how much should x be? So 8 is same as 2 to power 3. So then this is same as saying that x is equal to 3. So logarithm 8 in base 2 is equal to 3. And also some properties of logarithms. Let me also mention some properties of logarithms. So first of all, the domain. What is the domain of logarithm? Domain of y equals, let's say, log x in base a is d equals 0 to infinity. Domain is the set of positive real numbers. And what about the graph? The graph looks like this. In the case that a is bigger than for a bigger than 1. And it looks like this. If a is between 0 and 1. So you don't see this one, so let's see. In the case that a is between 0 and 1, the graph would look like this. And you also know some other basic properties of log. For example, you know that log xy in base a is equal to log x in base a plus log y in base a. Log x to power m in base a is equal to m times log x in base a. And log x over y in base a is equal to log x base a minus log y base a. Log 1 in base a is 0, and log a in base a is always 1. And there's also change of base formula. Change of base formula, which says log x in base y is equal to log x in base a over log y in base a. There is also another formula. We call it formula number 8, log. Let's say if the argument here has some power and the base also has some power. Let's say log x to power m in base a to power n. Well, we said that we can take this m out as a coefficient in front. What about this power n? This power appears in the base, so we can still take this out, but this time as a denominator, okay? So this will be same as m over n times log x in base a. Okay, so if you just have power here, you can take it out as numerator. If there's also power here, you can still take it out, this time as denominator. So for example, if you want to find log 27 in base 9. Log 27 in base 9, so this is same as log 3 to power 3 in base 3 to power 2. So I can take this one out as a numerator, this one out as denominator. So this is 3 over 2 log 3 in base 3. And then this is 3 over 2 times 1, right? We said log a in base a is always 1. So 3 over 2 times 1, which is 3 over 2. All right, so these are important concepts that you learn in pre-calculus. And one last thing I want to remind from pre-calculus is about trigonometry. So you spent a few weeks in pre-calculus learning trigonometric functions and their properties. So let me remind you quickly about them as well. Trigonometry. So if you remember, for trigonometry, you have to always work with unit circle. So this is, let's say, 1 and 0, right? And let's say you have two directions, positive direction and negative direction. So positive direction is the counterclockwise direction, negative direction is the clockwise direction. So let's say if you have an angle theta here, and you have some point here. So normally on the unit circle, normally we denote it with P sub theta. Now this point here has two coordinates, and the x coordinate is called cos theta, and the y coordinate is called sine theta. Okay, so any angle that you have, first you have to determine your angle. If it's positive, move counterclockwise. If it's negative, move clockwise. And once you have your angle, find the point on the unit circle called P sub theta. The x coordinate is called cos theta. Y coordinate is called sine theta. So for example, let's say if you want to find cos 90 degrees and sine 90 degrees, how can you do it? So normally in trigonometry, we use radians, and you remember the connection between radians and degrees. So you know that pi radian is equal to 180 degrees. So this is the connection between radians and degrees. Now, let's say if you want to find a cos 90 degrees and sine 90 degrees, for example, this example, find cos, let's say, pi over 2 and sine pi over 2. So we need to draw this circle, and then, so this is 90 degrees. And then this point here, which is going to be, so what is this point here? So do you remember this is the unit circle. So this length is 1 and it's on y-axis. So the x coordinate is 0, y coordinate is 1. So x coordinate, we said, is cos of the angle. And this one is the sine of the angle. So cos pi over 2 is 0, sine pi over 2 is 1. So remember that this is the positive direction. So if you want to move 90 degrees, we have to always start from here. It's always our starting point. We move, because it's the positive angle, we move counterclockwise. 90 degrees will be here. We will find the point on the unit circle, which is 0 and 1. And then the x coordinate is cos of the angle, and y coordinate is sine of the angle. Okay, and then tan theta is defined as sine theta divided by cos theta, and cot theta is defined as cos theta divided by sine theta. And you know that we have some identities. Or first, let me mention the table. We have table here. A table of trigonometric functions. Let's say cos theta. And then you have sine theta, tan theta, cot theta. Now, if theta equals 0, cos is 1, sine is 0, tan is 0, cot is undefined, because 1 over 0 will be undefined. If theta equals 30 degrees, which is pi over 6, then cos is root 3 over 2, sine is 1 over 2, tan is 1 over root 3, and cot is root 3. If theta equals 45 degrees in radian, will be pi over 4. Cos is 1 over root 2, sine is also 1 over root 2, and tan and cotan are both 1. If theta equals 60 degrees or pi over 3, then cos is root 3 over 2, sine is 1 over 2, tan is root 3, and cotan is 1 over root 3. And finally, if theta is equal to 90 degrees or pi over 2, then cosine will be 0, sine will be 1, tan will be undefined, and cotan will be 0. Okay, and then you learn also about some identities, trigonometric identities. Trigonometric identities that you learned in pre-calculus. So, of course, the most famous trigonometric identity in the world, I think, is sine squared theta plus cos squared theta equals 1. 1 plus tan squared theta equals 1 over cos squared theta, which is also called secant squared theta. So secant theta means 1 over cos theta. So instead of 1 over cos squared theta, we can say secant squared. And also 1 plus cot squared theta is equal to 1 over sine squared theta, which is cosecant squared theta. And what else can we say? Let's say sine 2 pi n plus theta is equal to sine theta, and cosine 2 pi n plus theta is equal to cos theta. So here n is an integer. So 2 pi n plus theta. 2 pi means 360 degrees, which means rotating the full circle once. So let's say if you're at some point with let's say at some angle theta, let's say you are here, right? And now let's say you move 360 degrees and you come back here. So this angle is theta. It can be also denoted by, let's say, theta plus 2 pi. So theta plus 2 pi means you are still in the same location, but you just rotated a full circle once, and then you came back to the same location. So because you're in the same location on the unit circle compared to before, so the sine and cosine will be still the same. Or let's say if I have theta plus 4 pi. Theta plus 4 pi means, again, you're at the same location, just rotate the full circle twice. Because remember, 2 pi means rotating full circle once. So 4 pi means rotating full circle twice. And etc. So sine 2 pi n plus theta is sine theta, cos 2 pi n plus theta is cos theta. So 2 pi n plus theta means you're at theta, but you're rotating full circle n times, and you come back to the same location as before. So you still have same sine and cosine for your angle. Okay, so what other properties? Did you see in pre-calculus? So fourth property, let's say sine pi half minus theta is equal to cos theta. Cos pi half minus theta equals sine theta. So these identities of this form, there are lots of them. You know, you can always draw the unit circle. So this is, let's say, theta. This is pi half minus theta. Now let's say if I compare sine and cosine of this angle, so this is cosine pi half minus theta. This is same as sine theta itself. And similarly, so you see this length is same as this length. And I don't want to make the picture too messy, but similarly, sine pi half minus theta, this length is same as this length here. Cosine theta is same as sine pi half minus theta. Cosine pi half minus theta is same as sine theta. Or let's say if you have, for example, sine pi plus theta, sine pi plus theta will be same as minus sine theta. Cosine pi plus theta is same as minus cosine theta. How can we see this? Or these two together, but by the way, means that tan pi plus theta is same as tan theta, and cotan pi plus theta is same as cotan theta. See, when you add pi to your angle, sine takes an extra minus, cosine takes extra minus, so the ratio will not take extra minus because minus will cancel with minus, right? So that's why we say tan pi plus theta is same as tan theta, because when you divide this equation by this equation, left hand side by left hand side, right hand side by right hand side, minus signs cancel, and then tan pi plus theta is tan theta, cotan pi plus theta is cot theta. So how can you see this property? So this property is also easy to observe. Even if you draw the unit circle. So this is theta, and this is pi plus theta. So let me again do it, let's say, for sine theta. See, sine theta means this length here. And then this length here would be sine pi plus theta, which is same length as this. So this length and this length are the same, but one of them is above x-axis, one of them is below x-axis. So that's why we are saying that sine pi plus theta is minus sine theta. Right? Because one above x-axis is positive, one below x-axis is negative. But the lengths are the same. So if the two lengths are, if two numbers have same magnitude but different signs, so for example, 2 and minus 2, both of them have magnitude or the absolute value of 2, but opposite signs. So then we can say one of them is equal to the minus the other one. So this length is sine theta, this length is sine pi plus theta. They have same length but opposite signs, so one of them is the minus of the other. And similarly, you can write it for cosine as well, or we have more identities of this type. We have exercise, write more identities of the types of identities. Four and 5 above. So there are more identities of this type, 4 and 5. So for example, sine, I don't know, let's say 3 pi half plus theta. What is it? Cos 3 pi half plus theta. What is it? Or I don't know, sine 3 pi half minus theta. What is it? So cosine 3 pi half minus theta. What is it? And so. So we have more identities of this type. You can write them as exercise. But we still have some more identities. So let me say 6. For example, sine theta plus or minus alpha. You saw that this is sine theta cos alpha plus or minus cos theta sine alpha. So when I say plus or minus, and here plus or minus, means if there's a plus sign, you have to match it with this plus sign. If it's a minus sign, you have to match it with this minus sign. And for cosine theta plus minus alpha is equal to cos theta cos alpha minus plus sine theta sine alpha. So again, this means if it's plus, you have to match it with this minus. If it's minus here, you have to match it with this plus. And tan theta plus or minus alpha is equal to tan theta plus or minus tan alpha divided by 1 minus plus tan theta tan alpha. Another identity, which is the immediate conclusion of 6, sine 2 theta. Sine 2 theta is 2 sine theta cos theta, right? You just need to equate theta and alpha, like sine theta plus theta. 2 theta means theta plus theta, sine theta cos theta plus cos theta sine theta. Then you'll get 2 sine theta cos theta. And then cos 2 theta. So that one again, cos theta minus sine theta sine theta. Cos theta means cos squared theta minus sine squared theta. And this one we can also write it as 2 cos squared theta minus 1. We can also write it as 1 minus 2 sine squared theta. So cos theta is equal to 2 cos squared theta minus 1 is also 1 minus 2 sine squared theta. And tan 2 theta is 2 tan theta divided by 1 minus tan squared theta. Again, you just need to replace theta with alpha. We have to basically replace that with alpha or equate them, in other words. Tan theta plus theta, which is tan 2 theta. And you get this formula. And for half angle formula, so these are called double angle formulas. And for half angle formula, I can say sine theta over 2. So here, if you change theta to theta over 2, so this becomes 1 minus 2 sine squared theta over 2, and the left-hand side becomes cos theta, right? So because if you change theta to theta over 2, 2 theta becomes theta. In the double angle formula, if you change theta to theta over 2, this becomes theta, cos theta, this becomes sine squared theta over 2. And then you can solve for sine theta over 2. And then this will be 1 minus cos theta divided by 2. And then you have to take square root with plus minus sign. So plus minus this. Depends on theta. Sometimes we have to accept plus. Sometimes we have to accept the minus. And for cos theta over 2 is plus or minus root 1 plus cos theta divided by 2. And law of cosine is another important rule you've learned in pre-calculus. So if this is, let's say, angle A, B, C, and this is side A, B, C, so you know that A squared is equal to B squared plus C squared minus 2BC cos A. And similarly, you can write for other sides, you know, B squared equals A squared plus C squared minus 2AC cos B, and C squared is equal to A squared plus B squared minus 2AB cos C. This is law of cosine. And law of sine. You know that A over sine A is equal to B over sine B is equal to C over sine C. This is law of sine. And also inverse trig functions. You also saw inverse trig functions. Definitions and properties. You know, for example, sine inverse of, let's say, A equals theta. What does that mean? Sine inverse of A equals theta means that sine theta is equal to A, and theta has to be between minus pi over 2 to pi over 2. So this part is obvious, right? We just, based on the definition of inverse of a function. Remember what did we say about inverse of a function? It interchanges input with output. So if sine inverse of A is equal to theta, then sine theta has to be A. But what about this part? Why do you think we have to also add this part? So because previously we said f of A equals B, is f inverse of B equals A. Why do we need to add this part? So that part is added in order to ensure that the function is one-to-one. Because remember, for invertible functions, you know, we are talking about inverse of a function. For invertible function, we need the function to be one-to-one. But sine theta, the function, or y cos sine x, basically, it's not one-to-one. sine x is not 1 to 1. Because, for example, it has lots of repeated outputs, right? So, for example, sine 2 pi plus pi over 6 is same as sine pi over 6. So it has lots of repeated outputs. But although the function is not 1 to 1, if we change the domain to be between minus pi over 2 to pi over 2, let me sketch the graph of sine x. So this is the graph of sine x. And as you can see, it's not 1 to 1 because it doesn't, for example, pass the horizontal line test. Remember, if you draw a horizontal line that passes the graph more than once, then that means your function is not 1 to 1. So this function here is not 1 to 1 if we consider the domain to be all real numbers. But if I change the domain, so whenever we have a function which is not 1 to 1, it's quite possible that after changing the domain, the function becomes 1 to 1. So if I change the domain to minus pi over 2 to pi over 2, this is where these numbers are coming from, minus pi over 2 to pi over 2. Then the function becomes 1 to 1. So see the function, if the function looks like this, then it is 1 to 1. So we are requiring the input of the original function sine x to be between minus pi over 2 to pi over 2 so that the function is 1 to 1. And then we can also talk about inverse of the function. Okay, so this is why we are requiring theta to be between minus pi over 2 to pi over 2. And similarly for cos inverse A equals theta means, I can write this way, it's equivalent with, or I can say means cos theta equals A, and theta this time between 0 and pi. So for cos theta, this is cos theta, again, see it's not 1 to 1, right? Draw a horizontal line, passes the graph at many points. But if you consider 0 to pi, this part, then the function again becomes 1 to 1, right? So if I delete the rest, see, now it passes the horizontal line test if I delete this part. This is minus 1, this is 1. So again, for cos theta, we have to change the domain to 0 and pi, and then the function becomes 1 to 1. And similarly for tan and cotan, so tan inverse A equals theta means tan theta equals A, and theta between minus pi over 2 to pi over 2. And cot inverse A equals theta again means that cot theta equals A, and theta between 0 to pi. So for example, let's say if you want to find sine inverse of minus 1 over 2. Sine inverse of minus 1 over 2, if I let's say put it equal to theta, this is equivalent with saying that according to what we said, I just erased it a few seconds ago. For sine inverse, we said sine inverse A equals theta is same as saying that sine theta is equal to minus 1/2, and theta between minus pi over 2 to pi over 2. So sine of which angle is equal to sine of many angles are actually minus 1/2. Because if you draw the unit circle, if you want sine to be minus 1/2, remember sine means the y value, right? So if the y value you want it to be minus 1/2, your angle could be here or could be here. So the original angle is, let's say, pi over 6. For pi over 6, the sine is 1/2. Now, if I want to be here or here, so that means either pi plus pi over 6, or this one, we can do it with 2 pi minus pi over 6 or just minus pi over 6, right? So there are many angles with sine minus 1/2. One of them is pi plus pi over 6. One of them is 2 pi minus pi over 6. One of them is minus pi over 6, which has the same location as this one. Another one, let's say 2 pi plus pi over 6. This is pi plus pi over 6, but if I add 2 pi to it, I will still the same location. Remember, we said adding 2 pi means rotating full circle once. So you'll be still in the same location. So 2 pi plus pi over 6. 2 pi plus pi over 6. Or other representations for this point or this point. But so there are many angles with this property, but only one of them is between minus pi over 2 to pi over 2 and has this property. And that is the value of sine inverse. So which angle? So basically minus pi over 6. Minus pi over 6. Theta equals minus pi over 6 satisfies sine theta equals minus 1/2, and theta between minus pi over 2 to pi over 2. Okay, what about, let's say, cos inverse of minus 1/2? Cos inverse of minus 1/2, again, if I put it equal to theta. So this is same as saying that cos theta equals minus 1/2. And theta this time has to be between 0 and pi. So if you look at your notes, you will see that, for cos inverse, we said if we put equal to theta, and cos theta has to be equal to a, and theta between 0 to pi. So which angle between 0 to pi has this property? You draw the circle. Cos means the x value. If you want the x value to be here, minus 1/2. So your angle could be here or could be here. So, but we are looking the one between 0 to pi. See, there is also one solution here, but in the context of cos inverse, we are not looking for that solution. We're only looking for a solution between 0 and pi. So the only solution will be this solution here, which is pi minus pi over 3. Why pi minus pi over 3? So see, theta equals pi minus pi over 3 satisfies cos pi minus pi over 3 equals minus cos pi over 3. Right? This is because of cos pi minus theta equals minus cos theta. And then So cos pi minus theta equals minus cos theta. So cos pi minus pi over 3 equals minus cos pi over 3, which is equal to minus 1/2. And of course, pi minus pi over 3 is between 0 and pi. So that means cos inverse of minus 1/2 is equal to pi minus pi over 3. Because it satisfies both of these conditions, pi minus pi over 3. Cos pi minus pi over 3 is minus cos pi over 3. Because of this identity, remember we said, I told you some identities of this type, and I said some of them you can write as exercise. So one important identity is this: cos pi minus theta is minus cos theta. So cos pi minus pi over 3 is minus cos pi over 3, which is minus 1/2. And the angle is also between 0 and pi. So cos inverse of minus 1/2 is pi minus pi over 3. So one common mistake is that some people think cos inverse of minus 1/2 is minus pi over 3. See, minus pi over 3 cannot be the answer. See, minus pi over 3 itself is here. Minus pi over 3 will be here. Minus pi over 3, and this is pi over 3. So the value of cosine here in the fourth quadrant, minus pi over 3 will be in the fourth quadrant. The value of cosine in the fourth quadrant is positive because the x value is positive. Remember, the value of cosine is the x value. The x value here is positive. So if the x value is positive or cosine is positive, you cannot have minus 1/2, right? So minus pi over 3 is the fourth quadrant. Cosine is positive there, so the answer of this cannot be minus pi over 3. But when you say pi minus pi over 3, you will be in the second quadrant, and cosine will be negative there. And this is the solution that we are looking for. All right. And another property you saw for inverse trig functions. For example, sine inverse of some number a plus cos inverse a is equal to pi over 2 for every a between minus 1 to 1. Cos inverse of minus a is pi minus cos inverse of a. For a between minus 1 to 1. And sine inverse of minus a is equal to minus sine inverse of a. So you saw the proofs for these properties in pre-calculus without using derivatives. But in this course, remember I told you about applications of derivatives, that we'll see different types of applications for derivatives. One application for derivative that we'll see is the proof of these properties. So new proofs for these properties. So let me say note, see proofs of these properties. I mean these three properties here using derivatives. You'll see that with derivatives, it's much easier to prove compared to the proof you saw in compared to the proof you saw in Math 100 or pre-calculus. So that was not very complicated either, but with derivatives, it's very easy. So we will see that just derivative of this function, we'll see it's 0. And if derivative is 0, we see that the function must be a constant function. And once we know it's a constant function, we can use any a value between minus 1 to 1 to find which constant it is. For example, a equals 0, we plug here, we'll see it's pi over 2. I'll give you the details later when we'll do the applications of derivatives and mean value theorem. Okay, guys, so these are the important concepts that you saw in pre-calculus. So yeah, we spent our lecture today about for the review of the important concepts of pre-calculus, and I think it was okay because we will need them in this course, right? So of course I didn't have time to cover one full semester in one lecture, but I tried to give you the important parts that we need in this course. So for example, we see that when you want to do the limits, we will deal with piecewise functions. So you have to know about the concept of piecewise functions so that when you want to compute the limits, you know how to deal with it. Or inverse functions, for example, derivative. We will see derivative of inverse functions. So of course you have to know about the concept of inverse function and what the inverse function is in order to learn the derivative of an inverse function. Or lots of examples that we'll do for derivatives and limits will involve trigonometric functions or some identities that we wrote here. So you have to know about those functions, trigonometric functions, and the identities in order to be able to find the limits or do the calculations to find the limits or derivatives, etc. Right? So so that's why now I decided to spend this lecture on the review for pre-calculus, and yeah, make sure you keep the notes for this lecture until end of the semester, because some of these will use maybe next lecture, and some of them will use them later during the semester. So I think it's good to keep the notes and just come back to them whenever necessary during the whole semester that we have ahead of us. Many of these will be used even in the next course, Math 114 as well. Again, Math 114, you will deal with functions, inverse functions, trigonometric functions, trigonometric identities, etc. So you can also use them in that course as well. Okay, guys, so thank you, and see you.